Welcome to Pharmaceutical Calculations, a Conceptual Approach, Lesson 12, Part 1, Mixture Problems in Pharmaceutical Sciences. Today's objectives are to identify the kind of variables that are preserved in mixture problems, construct equations that represent the initial and final state of a mixture problem, and solve these equations to determine the values of variables that are involved in a mixture problem. This description should provide the background to understand the empirical and obscure method of alligation alternate and hopefully replace it. But let us take a more detailed look of this novel method. At the end of our description, we should have a very powerful method in our hand. So mixture problems are special rate problems in which the composition of a mixture remains constant with time. We always have two types of variables that are used in the form of amounts, but the second type of variable is also used to form a rate with respect to the first variable. Let us take a look of some representative variable types. One variable type could be the mass of a drug, and you could have M1, M2, and so on and so forth. Another type of variable could be the volume of a solvent, and again you could have V1 and V2 and V3 and so on and so forth. The rate that I mentioned over here in this case is the ratio of the mass of the drug over the volume of the solvent, and therefore we could have drug concentrations in solutions here, C1, C2, C3, C4, and so on. Now the characteristic of these variables is that there is a preservation of their values before and after combining them. Before, we actually mean before mixing them, and after, we actually mean the final state after the mixing process. We could construct a total of three equations, one for each type of variable and one containing the rate. Let us take a look of the kind of equations we could have here. So from the first type of variable, we have M1 plus M2, and I kept these equations for two components just to simplify our explanations. The second, and of course when you mix M1 and M2, you're going to have a final mass of drug. The preservation of two variables here, what we mean is that if we mix 2 grams of drug plus 3 grams of drug, we're going to end up with 5 grams of drug here. The same goes for the solvent. V1 plus V2, after I mix these two volumes, I would end up with a final volume that is exactly the sum of the V1 plus V2. So if I had here 20 ml and 25 ml, this would be exactly 45 ml. It wouldn't be 44 or 43. So the requirement of these variables, of this type of variables, is that there's no chemical interaction that will result in a shrinkage of the volume, in this case, for example, or an expansion of the volume. So there's no chemical interaction that would cause the final volume to deviate from the summation of the two volumes. And of course, the third equation contains the rate, and that would be V1 times C1 plus V2 C2 equals to the VFCF. So the left side of our equations here is always the initial state, and they contain the variables before mixing. And the right side of our equation contain the resultant variable after mixing. Because the rate is coming out of the two variables, in order to determine the relative amounts of these variables or the relative values of these variables, we only have to solve 2 out of 3 equations. Let's say equation 1 and 3. So this is the general description of mixture method for n components. We have equation 6.1, which basically describes the one type of variable, which is VA. So we have VA1, VA2, VA3, and after we mix them, we have VAF. V here stands for variable, not for volume. And here it could be the volume of a solvent, of course. Now VB is the second type of variable, and that could be the mass of a drug. So you could have VB1, VB2, VB3, and after you mix them, you have VBF final. The rate here is the ratio of VB over VA. So it could be the mass of the drug in the volume of solution or solvent here. And the equation that includes the rate is equation 6.3 here. So this is the general form of mixture problems for n component, n number of components. It could be 100 components, it could be 5 or 3 components. Okay. Now the purpose of this slide here, I just wanted you to know that mixture problems are not only describing composition of chemical compounds. You could use mixture problems to solve problems related to pharmacoeconomics. For example, the rate could be the cost per unit item, or problems related to pharmacokinetics. And we're going to take a look of one example relating to composition and one example relating to pharmacoeconomics. But always remember how we solve these kind of problems. We first identify the type of variables. We then construct equations based on the principle of properties preservation. And finally, we solve the system of linear equations to determine the specific values of these variables. So let us take a look of our first example here, example 6.1. Here, we are mixing two lipids, cholesterol, in which the molecular dimensions are given here, and DOP, this is a phospholipid. Again, the dimensions are given. And we have a total of 10 to the 16 molecules. Now, these two molecules are mixed in a certain ratio such that the combined molecular area is 40.4 angstrom square per molecule. This ratio, at this ratio, their interaction is ideal. In other words, there is no attractive or repulsive interaction between the two. That's the meaning of ideal here. And of course, the problem here is stated does not describe the whole detail of the experiment. For example, you mix these two lipids in water. So when you mix them in water, they do accumulate at the air-water interface and they form a lipid layer. And that's why this is very important here. Now we also have here several constants, the Avogadro number, and of course the molecular weights of the two lipids. What we need to do first is identify the type of variables that are combined, construct equations, and then solve the system of equations to determine the amounts, the relative amounts of these two lipids. Okay, so let us proceed to the first task. We have the molecular dimensions of the two molecules before mixing, and after mixing is the AF. And we also have the total number of molecules of these two lipids. We just don't know at this point how much of each is used. So we need to determine N1, the number of molecules of the cholesterol in this case. 1 stands for cholesterol and 2 for DOP. So our first equation involves the first type of variable, which is the number of moles of cholesterol and the number of moles of DOP that are combined to 10 to the 16 number of molecules. The second type of variables involves the surface area occupied by these molecules. Not the molecular surface area, not per molecule, but the total surface area when you're going to combine these molecules. Now, when I divide this dimension, this D, over the number of molecules, I get actually the molecular dimension A. So that's the rate in this case. So I have equation 6.4 as my first equation, and equation 6.6 as my second equation. I need to solve the system of these linear equations to determine N1 and N2. Remember, A1 is given, A2 is given, AF is given, and NF is given. That's 10 to the 16, right? So I need, based on this, I have two equations, one equation here, second equation here, and I only have two unknowns. So I should be able to solve them nicely and determine the corresponding values of these two. So first, n1 plus n2 is equal to 10 to the 16. I solve for n1 and I substitute in equation 2. I solve equation 2 for n2. So here what I have, this is a1 and this is a2, and of course this is af. Okay, so I solve for n2 and I find that the number of molecules of DOP is 2.7 times 10 to the 25th. I substitute this value over here and I determine n1. So n1 is 7.3 times 10 to the 15. So the ratio of these two, n1 over n2, is 2.7 to 1. And this is very important because that goes back to physical chemistry or physical pharmacy if you wish. We are dealing with partial molar properties. And in physical chemistry, what this means is that some properties of the system are intimately related to the composition of the system. In other words, what I'm saying is that this ideal interaction, when you change the ratio of mixing of these two molecules, will change as well. It won't be ideal, it could be attractive or repulsive. So these are the partial molar properties. And we're going to see one exercise at the end. We're going to describe one exercise there that exactly relates to these partial molar properties. Okay? So now what remains is to determine the relative moles of each one and eventually the gram amount. So to determine the moles of each compound, all we have to do is to divide the number of moles, and when we do that, we end up with moles of cholesterol as 1.21 times 10 to the minus 8, or 12.1 nanomole, and the moles of DOP is 4.48 times 10 to the minus 9 mole, or 4.48 nanomole. Okay, notice the difference here in the exponent. To find the mass in grams, we need to use the molecular weight of each compound. So here we have used the Avogadro number. And now to calculate the mass of cholesterol, we need to multiply the number of moles times the molecular weight. And we end up with 4.69 micrograms of cholesterol and 3.34 micrograms of DOP. So when I mix these two components in these amounts, I get an ideal interaction in the mixed lipid layer. Okay? Now, why is studying mixed lipid membranes so important for us? Simple. Because drug absorption and distribution takes place by passive diffusion of drug molecules through lipid membranes. We would like to know the effect of cholesterol on phospholipid membranes as it affects their fluidity and rigidity. It is known that cholesterol affects the sealing properties of membranes. And here I've included a representative schematic of a lipid bilayer in the insert here. So we have a cell membrane. This is a section of phospholipid bilayer, a section of a membrane. Imagine a drug molecule that has to be hydrophobic if it's going to be inserted into the lipid bilayer and hopefully go through transcellularly inside the cell, and of course get out of the cell into the other side of the membrane, into the blood, for example. So this is why example 6.1 is very important for us. The second example of mixture problems, as described in example of 6.4, is related to pharmacoeconomics. Let us assume here that you are the owner of a store and you would like to have these two multivitamin brands in your store. Now, you have an available budget of $1,050 and you want the cost, the final average cost, to be maintained at 3.5 cents per tablet. each brand has a different cost. So the brand 1 comes at a 4.50 cents per tablet, and the brand 2, R2 here, comes at a 2.45 cents per tablet. The question here is how much of each brand should be purchased. And again, this is a mixture problem. We work by first identifying the two types of variables, second construct equations, and third solve the system. So first let us identify the type of preserved variables here. We have the rates, we're given the rates here, and we're given the budget. And of course we are asked to provide the number of tablets that can be purchased from each brand. So our first variable is the number of tablets, and I'm going to call this T, capital T. And here I'm going to calculate the TF, or the final number of tablets that can be purchased within the available budget, which is CF here. And I know the final average cost rate. Okay, so dividing the available budget over the desired cost rate, I end up with 30,000 tablets. So with this amount of money, at this desired average cost rate, I can purchase 30,000 tablets. So my first equation should be T1 plus T2, and that would be the number of tablets from brand 1, the number of tablets from brand 2. That would be equal to 30,000 here, tablets. Okay? Now the second type of variable is the cost. So how much dollar amount shall I spend for the brand 1, a dollar amount spent for the brand 2, and that's the desired cost, or the available budget actually, right? So the C1 and C2 does not exceed the CF. And of course, now that I have the rates, which is defined as the cost over the number of tablets, I can construct equation 611, which is R1 T1 plus R2 T2 is equal to RF TF. Again, T1 is the number of tablets from brand 1, R1 is the cost rate of brand 1, R2 is the cost rate of brand 2, T2 is the number of tablets of brand 2, RF is my desired average cost rate, which is 3.5 cents per tablet, and of course TF is the number of tablets which we have calculated, and it's actually 30,000 tablets. So now we need to solve these two equations and calculate T1 and T2, and of course after that we can calculate how much dollar amount is spent for the number of tablets of brand 1 and how much dollar amount is spent for the number of tablets of brand 2. So having my equation T1 plus T2 equal to 30,000, I solve for T1 and I substitute in equation 611, and I end up with the number of tablets of brand 2, 14,634. And then I go and substitute over here and I get the T1. So with the available cost at the desired average cost per tablet, I can purchase 14,634 tablets of brand 2 and 15,366 tablets of brand 1. Now the dollar amount spent for the purchase of brand 1, and I can do that by multiplying the number of tablets now that I will purchase, which I know, that's the one there, right? Times the cost of brand 1 per tablet, which is 4.5 cents. I end up spending $691.47. For brand 2, I do the same thing. I multiply the rate, the cost rate times the tablets purchase of T2, which is 14,634, and I end up with $358.53. Finally, I have included a number of exercises for your practice. Example 6.2 is a mixture composition problems, and most of the exercises that I have included for your practice are mixture composition problems. The difference from example 6.1 is that here you are given the composition and you are asked to determine the nature of the interactions of these two lipids. Is it repulsive or attractive? And of course you are given the answer, just to verify that you solved the question the right way. Now example 6.3 is related to Raoult's law. So in this case you may have only one type of variable, a very interesting and realistic problem. Now exercise 6.5 is not a mixture composition problem. It is actually a mixture problem related to drug release or pharmacokinetics. A very interesting one. Exercise 6.6 and 6.17 are very interesting compounding problems. They are mixture composition problems, as well as the 6.18. And at this point, I would like to thank you for your attention. Until next time.